Okay. Yes, this is a Windows computer, so it's just as bad as you think. But PowerPoint works really well, so. Okay, so I'm going to open it up today, I guess. I'm going to be talking about understanding the terrain of DevOps, and I think that's pretty appropriate given the schedule I saw here today. It's really going to be about, I think for a couple of years, doing DevOps, quote unquote, as correct or incorrect that may be, was pretty easy because you knew Chef or Puppet and used Chef or Puppet, and as long as you did that, that was pretty much all there was to it from a technical side of things. And then no new tools really came out for a long time, and then I feel like in the past 2 years or so, it's gotten really crazy, and a lot of tools have come out, and I get a lot of confusion, of what people should use and not, what they shouldn't. And I get asked a lot, things like, oh, should I use Serf or should I use Docker? And it's kind of like, they don't overlap in the slightest. So, I'm trying to address those questions with this talk. So this is me. The most valuable piece of information on this slide is the Twitter handle. If you have any questions or want to get a hold of me during the conference, it makes my phone vibrate even if I don't want it to, so I'll know if you ping me. I started work for this company, and we're a DevOps tools company, so basically what we like to do is work with a lot of companies and see where they have DevOps pains and try to see if we could solve a tool, build a tool to solve their problems, because having worked in various companies, I really believe that being in a company, you can't really build a good DevOps tool because it doesn't align most of the time with what your business wants. So you build a duct tape solution and you might open source that, but you don't really make it as general or as applicable to the industry as you can. So instead, I like to go around and see what people are doing, see how they're solving problems, and maybe if I could get permission, use some of their inspiration to build open source tools to do the same thing. And to date, we have three tools or pieces of software that are out. There's Vagrant, which I'm sure most of you are familiar with, Packer, of which there's 2 or 3 talks at this conference about, and there's Serf, which I'll be spending the most time probably talking about today, mostly because the other 2, there is a dedicated Vagrant talk today, and there's a talk about Packer, so I'll talk about Serf. And there's a couple more coming out in the next couple months. Okay, so I'm going to start out general and kind of move to more specific and more technical. And so let's start with the application lifecycle. And I kind of want to describe what the application lifecycle is and what problems there are with this process of getting an application from development to production, and how kind of DevOps comes in here to solve these problems. So I split this down into 3 categories, and sometimes in certain companies 3 silos, and I just kind of go left to right and we'll see where we get. So the first kind of category I talk about is development. That's really where the process starts, and this is kind of the fun part because it's the part where things matter the least. You could use whatever you want. You could be as unscalable as you want. You could be backwards incompatible. It doesn't really matter. But there are certain traits that are important to development environments in order to be productive and to be happy kind of working. So 4 things that you kind of want in a development environment. You want them to be readily available. So whether you're working at a cafe or an office, or on a plane, or you're on vacation, you need to access your computer, you want to be able to work on things. And when I say readily available, I don't mean they has to be offline. There's a lot of web IDs coming out and stuff, which are pretty cool. But I just mean that you need to be able to access it without a lot of effort. Another trait you want is to be able to make changes and see those changes. So this is kind of the golden circle of what you want to achieve in a development environment. You want to code something, you want to save it, and you want to reload the page or reload an iPhone app or something and see the change. And this is something that PHP got really, really right. Very few things, but this is good. But this is really what you want to head towards, and it's really hard to do with things like, sometimes it's hard to do this with Ruby, sometimes it's very hard to do this with mobile applications, but if you could head towards this direction, this is where you want to get. And you want consistency. So consistency is really well described with this comic here. And the basic thing you want with consistency is you want to avoid this problem, which is that something works on your computer and something doesn't work on someone else's computer, or something works on your computer but doesn't work in production. And you really want to avoid this, because this problem is just a huge waste of time. Because, for example, using these bear bird things, if this happened, it could be the bird's fault or it could be the bear's fault. You don't really know. You don't really want to point blame. So then these two expensive engineers end up spinning their wheels for an hour trying to figure out whose problem it really is. And then at the end of it, they get it working. But that problem really shouldn't have existed in the first place. And then you want, on some degree, a level of collaboration and sharing. So even though programming a lot of times is a pretty solitary thing, or sometimes you're pair programming, but then it's solitary to two people, at least once a week or once a month or something, hopefully more than once a month, you want to share what you're working on and show people what you're working on, maybe get help from others. So there's some level of collaboration in the development environment, and you want to make this as easy as possible. So just as a summary slide, here's 4 traits I found just over the years that people really want in a development environment and want to head towards. And so that's the development aspect of the application lifecycle. And then we're going to head to deployment. So deployment is really just after development, it has to run somewhere. And so for the purpose of this talk, that somewhere could be a test cluster, staging cluster, or production. It doesn't really matter. It's all form of deployment. It's really from development to something more real. And this is a really important step, and also a huge pain. So there's you can break this down kind of into 2 different phases, so to speak, but the end goal of both is really to deploy something. So the first phase, there's the start configure server part, and if you've never seen this picture, that's Google's data center, but I think it's like 2 years old, so I think everyone's seen it by now. But in this phase, basically, you want to run a server somewhere. You have to, even if you're using something like Heroku, someone started a server somewhere. And then you want to install some sort of base software or base layer of configuration in order to run the application. And then finally, you want to deploy and run the application. So this might be broken down into a series of steps too. There's maybe a compilation step. Java, Ruby has one now with like Node for some reason. You want to get that thing on the server. You want to start it, and then hopefully as a second step, you want to make it live. Or to poke more fun at PHP, this could all be one step. Whatever works, man. But yeah, so you want these steps to kind of break down. And that's really deployment phase, and it's deceptive because it's really easy to define the problems and yet really difficult to solve them. I still haven't been in a company where deployment has been easy. Heroku makes things easy to a certain extent. I'm hoping Docker makes things a lot easier in this regards, but it's still today a huge pain. Okay, and then finally there's maintenance, the least fun, the most boring. And in the maintenance phase, the primary goal is that everything just has to keep running, but everything has to keep running while things are also changing, which is a little bit of a crazy request, but that's what we have to do. So this involves a few things. Of course, there's monitoring, and monitoring is all about anticipating problems and reacting to them before they hopefully become actual problems, but sometimes this sort of thing happens. There's the updating side of things, and when you're updating, there's 2 aspects to this too. You need to update, ops people want to update servers, they want to update, they want to apply security patches, they want to change the OS sometimes, they want to update software. And then there's the application side where developers want to deploy changes to the application, and those are sometimes at odds, but they both need to happen. And then there's orchestrating, and this is kind of a very overloaded term. A lot of people use orchestrating a lot, so I'm going to just define it a little bit more. By orchestrating, I mean you want to be able to do something like this. You want to be able to look kind of at the state of an entire infrastructure or a set of multiple servers. You want to make some decision and then affect the entire infrastructure. And so this kind of transcends just one shell script, because you can't write a shell script and run it on one server and expect to do these sorts of things. You need some sort of outside orchestration of sorts. And that really breaks down maintenance, which is also 3 bullet points, but infinite pain. So that really defines these 3 categories and really defines what I call the application lifecycle. And what's interesting is I've broken it down to this, and then if you think about it, these problems or goals and categories really apply to pretty much every application in existence, no matter what tooling you use. So whether you're developing a desktop application or a web application or a mobile application, there's some sort of operations involved and some sort of process involved, and this kind of generalizes that pretty well. If you're using something like Heroku, you still have these issues, except Heroku just tries to get rid of the second 2 columns for you, but they're still their problems, so they exist. And so why this is still important. So why is this important? Why am I even telling you this? This is important to understand DevOps a little bit more. And so DevOps is not a what is DevOps talk, by the way. But DevOps, of course, has cultural and technical components. I'm going to pretend the cultural ones don't exist because on a day-to-day basis, that's just not what I do. I work on the technical side of things. So we're just going to be talking about the technical side. So not to say the cultural side isn't important, but I'm not going to talk about it. But the goal of DevOps is to make that application lifecycle more efficient. People could say a lot of things about DevOps. They could make up some harmonious, holding hands sort of definition for it, or you could say that devs are actually doing ops themselves or something like that. But really, everywhere I've seen DevOps in place, the pragmatic, real goal for everyone that's aligned is just to make that application lifecycle more efficient. So developers want to get things through to the maintenance phase to deploy faster. Ops people want to be able to do maintenance easier. Business people also want the application to go out faster because it perhaps means they'll make more money. So everyone's goals are pretty well aligned, and so it's really no surprise that DevOps as a buzzword really succeeded. But how do we make this application lifecycle more efficient? It's the same way humans have been making things more efficient forever, and that's tools. So tools, basically, we do something crappy one time, or we duct tape something together one time, and we learn about it, and we kind of enhance and refine that process until we could get it into a form that is a tool. And these tools, reduce human error. We're humans, even if we do something 100 times, the 101st time we might mess up. It happens. Increases repeatability because repeatability because the knowledge is codified, and that's the most important step, is the codification of knowledge. Because if you think about it, for example, tools get rid of. Once you use a tool, you don't need to know how it works beneath that tool. Some people might say, you should understand how everything works, but with tools that simply isn't necessary, and it's not necessarily a bad thing either. Because, for example, let's think about compilers or something. Compilers are a tool so that we could build things faster. Do most people know how compilers are, making a lexical pass or a semantic analysis, or how that's turning into an AST that's turning down into assembly or some sort of bytecode? No, most people don't know, and it's really not important in the general case. It's the same thing with tools. Tools make it so that, for example, there's something like Vagrant. For the person who sets up Vagrant, yes, perhaps they need to understand how the servers worked or how software gets installed to set up a Drupal development environment. But when you then deploy that to your company of 200 Drupal developers, they don't know how that was set up, and it doesn't matter to them. But now you have this tool that they could then teach to other people, and it lets them focus on the higher level things, new problems, pretty much. So tools kind of push us forward. And so DevOps tools have to solve something, one or more things in this application lifecycle. So just like this hammer in the background here, just like there's a hammer, you basically need more than a hammer to build a whole house. So there's a lot of tools out there that solve a lot of problems. Yeah. And so it gets a little confusing because these tools are sometimes ambiguous, and that's okay. In that chart, sometimes tools solve more than one problem. Like, for example, if you think of Heroku as a tool, it gets rid of 2 entire categories, and that's totally okay. It's just a matter of understanding where the tool lies, and understanding this really helps you figure out what tools you need and where they belong in your organization. Okay, so we're done talking about general things, and now we're going to kind of do a little tour of tools on the technical side of things. And I'll mention a lot of things. I'll only focus on things that I work on, because I'm allowed to do that. But I'm going to kind of go lighter than normal on talking about Vagrant and Packer, because there's talks about it here, and I don't want to steal their thunder. And I also don't have a super amount of time. And I'm going to go in order. So I'm going to go from left to right, and I'm going to go in order here. So let's start with development. Development, perhaps is no surprise, is pretty synonymous right now with Vagrant. So let's talk a little bit about Vagrant. I think most of you probably know. I hope most of you know. I hope we're past that point. But if you don't, I'll describe the basic workflow or a high-level idea of what Vagrant is. The idea of Vagrant is that if you adopt it within your company, anyone in your company can clone any repository that was built at hopefully any point in time using any sort of technology. Whether it was a huge Java application, 15 years ago, or Perl, or nowadays perhaps it's Node, God forbid, or something. But you clone it out, and then you run Vagrant up, and you're ready to work, no matter what the technology is, and the workflow is the same, and the process is the same, and is therefore teachable to people and repeatable, and so on. And within that development category, I mentioned 4 problems or 4 goals, and how Vagrant kind of attacks these. On the readily available side, Vagrant works with any sort of kind of technology to run code it can. So there's virtualization providers such as VirtualBox, VMware, and recently Hyper-V. And on the more cloudy side, there's AWS, things like DigitalOcean, and as soon as Microsoft Legal checks off on it, Windows Azure. And the idea here is that you use what's best for you, and we make it pretty easily available in both cases. In the virtualization case, of course, you just need a computer that could run that, and then the cloud case, you just need an internet connection. You want to be able to make and see changes, so you want that golden circle. The way Vagrant solves this is it splits the concept between a host machine, which is the thing running Vagrant, and the guest machine, which is the thing running your code, which could be, again, a VM or another computer or a cloud thing. And it uses a synced folder abstraction in order to usually get a bidirectional sync of files. So it might use VM shared folders if they're available. It uses NFS if you choose to. And then recently there's rsync, which is currently one directional, but soon will be bidirectional. And then there's SMB, which is also bidirectional. So the idea, though, is that you, as a developer, really don't have to worry about how the files get there. Vagrant just provides a mechanism to make sure they do get there. Then there's consistency. And so the importance of consistency in Vagrant is really in its compartmentalization in a virtual machine or some other sort of sandbox that runs on Windows, Linux, or Mac. So whether you have someone who works on a Mac or whether you have the one person who refuses to even look at something other than Linux, you could get them to work in a consistent development environment because it works identically on every platform. And then recently, on the sharing side, the collaboration side, we released this sort of feature, Vagrant Share and Vagrant Connect, which, if you don't know about, basically, if you have a Vagrant environment up and running, you type Vagrant Share and hit Enter, and it'll give you a URL that routes directly to your virtual machine through any NAT or corporate firewall and stuff like that. And Vagrant Connect will actually give you a static IP that you could pretend is on a local network. And again, any packets that are sent to that static IP actually route all the way through to a virtual machine. So as an example, the internet here is pretty good, and assuming it's still running on my laptop, it didn't sleep or anything, you should be able to go to this URL, and it'll load up a directory listing, and that directory listing is actually my virtual machine on this computer right now. But you could do that with anything, so that's kind of neat. And this is this was super important because it just let people share their environment easier than others. A lot of companies now with this are getting rid of a lot of, they still have a staging area, but they're getting rid of dozens of staging areas because developers no longer need to push to a staging area to collaborate on APIs or work with mobile clients or stuff like that. They could just run the share thing and get a URL and work. And so Vagrant at its core is just really a technology-agnostic development environment builder that focuses on giving you a common workflow. So the important part of Vagrant is really the workflow, much less the technology. And so by technology-agnostic, I mean, it runs on Windows, Mac, Linux. It could run Windows, Mac, or Linux virtual machines as well. And then, if you have things like Docker within there, it knows how to deal with those. And that integration is getting just a lot better every day. And nowadays, it's also pretty popular. This slide's actually from 2 years ago, so it's a lot more popular nowadays, which is pretty cool. It's good to know, because it's good to know that if you learn something or invest in something, that it'll stick around and that it's well, adopted. And I'll leave the rest of the Vagrant talk to Paul, who I've never met but is here and is a committer on Vagrant. So, and then deployment. So then on the deployment side, I said it's complicated. I'm going to talk about a Packer just a little bit, because again, there's a talk there. But the deployment side is really complicated. So here's 6 things. I could have listed 50, but there's a lot of tools that are in this space. And if you break it down to the phases, there's a couple. There's the start, configure, server side of thing, and then there's the deploy and run software side of things. And if you look, there's like overlap there, which makes things more complicated. But I'm just going to focus on Packer a little bit, which is on the start, configure, server side of things. So Packer is almost a year old now, and in that year is actually used quite a lot, which is surprising to me. I didn't expect it to be adopted that quickly, because it took Vagrant years. But the idea of Packer is basically that it optimizes the slow parts of setting up a server by pre-building those into an image. And you might be thinking, like, images, especially if you've been doing ops for a long time, there's, in modern DevOps practices, there's kind of an anti-image stigma, and the DevOps movement in the past few years has historically been against making machine images, but it's kind of important to understand why, because there are good reasons. There's very good reasons, and it's important to understand those in order to avoid those problems. So I'm just going to talk about that. So with images, let me make sure I didn't make these slides. Yeah, no. So if you were doing ops like 10 years ago, images were pretty much the way things were done most of the time. And this made a lot of sense. The tooling wasn't very good. You had stuff like CF Engine 2 and some older technologies that were kind of just not very fun to use, even though they got the job done. So it was easier for people just to go in manually and set up a server and be done with it. And so what ended up happening was, when you had more than one server or a handful of servers, you would go into the server, set it up manually. Once it got to a state where it was working pretty well, you would just stamp it off and say, like, this is it, this is perfect. And you would save a disk image, and that would become your golden image, because it was gold. You set it up, and you would generally use that for the next business quarter. A business quarter was like a safe period of time to use something, because you were pretty confident that that image wouldn't mess up, earnings or have downtime during that quarter. That was the hope. And this is pretty frustrating, because as an ops person, you can't really get changes in there unless they're critical. As an application developer, if you have new dependencies or you need changes to the environment to run new features, you couldn't get those in there. Frustrating again, really hindering ability to ship. And so what ended up happening is, modern configuration management came around, and it became easy to simply ignore images. You got these kind of shadow ops deals happening where people were saying, okay, screw it, we'll just run our own servers, and we'll use configuration management to spin it all up from scratch, and we'll treat every server the same. So we'll start with a bare Ubuntu on every machine, and we'll just run Chef, and Chef will turn that stem cell into whatever I want it to be, and it'll be great. And it does. It works really great, and that's why people do it now. And the problem is, machine images also had a ton of benefits, and we've pretty much lost those benefits by ignoring them. So one of the benefits is super fast infrastructure deployment. So even in the simplest case, a Chef or Puppet run, for example, something stateless like Memcache or a web server, could still take, with all the basic monitoring and stuff you lay down on a production server, could still take 5 minutes maybe. A more stateful server like a database, or if you're deploying a web server that has a lot of dependencies, could take 10, 30 minutes. I've seen longer than that, but that's a little crazy. But it could take a long time. With images, if you have the slow parts baked in, you just launch the server, and that part's done. There's just a little bit of orchestration to do after that. And then there's also stability and testability. So right now, the way we test Chef and Puppet is we run Chef or Puppet or any config management. In a CI, we just run it against a new server, and if it succeeds, we assume it's always going to succeed, and that's going to be good. But the problem is that it's not safe against things like network changes. You don't really know the ripple effect of Chef and Cookbook changes. So if you say, like, yes, the load balancer role succeeded 3 months ago, it's super common 3 months later to try to spin up a load balancer and something fails for some silly reason. And with images, since most of it basically minimizes the surface area where things could fail. So you don't have that anymore. So basically what Packer does is it takes the slow parts of building servers, which are mostly this. If you were to get rid of this, servers actually set themselves up in less than a minute usually. And it kind of just gets rid of those by redoing it. So I'm actually going to skip these because I don't want to run out of time. But there's a Packer talk later of how it fits into the workflow. It could build images for all these things. And it could do it using these things. Okay, so maintenance. This is where it gets interesting because I get to talk about Serf, which is really fun to talk about. So there's a lot of things in maintenance category, but the thing is, Logstash has really nothing to do with like CF Engine. And the reason there's lots of things is they have lots of different purposes. They're solving lots of different problems. But the interesting thing is all these things really have a common goal, and that is really to be able to change things and move with some resiliency to failure, to either avoid problems or anticipate problems, to fix problems. But really the end goal is, could I ship my software safely? Could I ship this update safely? Is everything going to be okay? And one thing to help do this, and which I'm going to talk about today, is Serf. So Serf, the one sentence, buzzword packed description is this. I'll let you read it, I guess, because I don't like to read it. But even if you're a super smart guy or girl, and you read this, usually the response at the end is what? Like what? I read it, but I still don't know anything. So really the best way to think about it is that Serf manages membership and lets you know when membership changes, when things join, when things leave, when things fail. And what's funny is nowadays a lot of ops problems could actually be boiled down pretty nicely to membership problems. And as an example, the easiest example is a load balancer and web server. So in this case, for example, if you want to take that web server out of the cluster, let's say it's not failing, you want to take it out. How does the load balancer find out? And this has an easy answer without Serf, which is load balancers usually have health checks. The health check will figure out it's down and just ignore it. Sure. But that usually sometimes involves killing HTTP connections. So how do we gracefully get it out of there? How do we tell the load balancer, I want to turn off, web server 2, so finish any outstanding requests, stop it, and then turn it off. Again, a lot of web servers have this. So on the flip side, what if we're adding a node? How does the load balancer learn about the new node? How does it discover that? And that's really where Serf comes in. And you could think about this in terms of memcache clusters, database clusters, application configuration, trying to know where Postgres is, for example. And the way this works is every node runs a Serf agent. You register handlers with the Serf agent, which are any sort of shell script, and those handlers actually execute the business logic, which is things like add or remove a node from a load balancer. And the events that are sent to the handler are things like someone joined the cluster, someone left, someone failed, someone changed, and then there's user events, which are custom events, which I'll talk about. But how does Serf work? How does Serf know these things? How is it different from other solutions? And this is where it gets kind of interesting. So Serf uses a gossip-based membership cluster. And for those who don't know what a gossip protocol is, the best description or the best analogy I like to make is gossip-based membership is a lot like what would happen in the real world if there was like a zombie apocalypse happening in Salt Lake City right now. So if zombies were taking over Salt Lake right now and we're happily in here, we would find out probably because there'd be loud noises. Someone would run in from the library and tell us, and then we'd probably freak out. And a lot of people here are from Salt Lake, so they'd probably call their family and tell them there's zombies in Salt Lake, and there would be panic. But everyone would find out really, really fast. Another example is Twitter. You tell someone on Twitter, they retweet, it spreads out. Gossip-based membership's the same way. One node joins the cluster, it tells one or more other nodes, they tell one or more other nodes, and eventually the whole cluster finds out. And that eventually is kind of interesting, because a lot of people think, well, that sounds expensive or slow. It's actually very cheap and very fast. So one of the biggest Serf clusters that I know about right now is running 4,000 machines in EC2, and in that 4,000 node cluster, when they add one node to the cluster, it gossips, assuming no network errors, which is generally the case in EC2. Assuming no network errors, it reaches out across the entire cluster in about 200 milliseconds. So you add a node, and within 200 milliseconds, every node knows it was added and their event handler is fired. And that's pretty fast. And it's pretty cheap, too. So on the network bandwidth sort of thing, it uses, I think, 700 kilobits per second. So you don't even see it on your network graphs. Then on top of this gossip-based membership, there's failure detection built in. So I'm just about out of time, but I'll power through this. So failure detection, basically, instead of doing a heartbeat, which is kind of naive because heartbeats generally scale exponentially in terms of network traffic, what Serf does is it uses probability. It's a very probabilistic tool. So it uses probability, and the idea is that if every second I choose a random person to talk to and everyone chooses a random person to talk to, then probabilistically we've checked everybody. And so every second that's what Serf does. One node will choose a random member, and it's thousands of nodes, ask them, are you alive? Basically do a ping and an ACK. And if it says I'm not alive, then it's a little bit smarter. It asks a few other random nodes. It chooses like 3 random nodes and asks them, can you talk to this person? Maybe I'm just having networking issues. And if they say no, then that node broadcasts across the entire cluster that he or she suspects. There's no gender to computers, but the computer says, I suspect that this person is dead, and that gives that red node a certain amount of time to receive that message and refute it. And if the node doesn't refute it, then it's actually dead. So we take a very defensive approach to detecting if a node is dead, which takes a little bit longer, but again, using the 4,000 node cluster as an example, if I were to just punch one of the servers in the face and it died, the whole cluster would find out in about a second, which is pretty good. And you could turn off a lot of those checks, like don't suspect them, don't ask others if they're dead, just assume they're dead, and then you'll get the 200 millisecond thing. And then finally, there's custom events. So we have this gossip-based layer and a way to communicate very efficiently among thousands of nodes very quickly, but probabilistically. And we expose something called custom events to do that. So you could actually tell any node to say, send the deploy event to the entire cluster, and then the event handlers will be invoked and they could do things. So a lot of people are using custom events, for example, to trigger Chef or Puppet runs. Instead of running them on a cron, I update Chef or Puppet, and then I run an event. And the latest version of Serf that came out last week actually has a request response mechanism. So you could send an event efficiently across the pool and say, send me an ACK when you finish running, or that you got the message and you will start running. And so that way you could kind of defeat the probabilistic nature by retrying, basically, if it failed, or targeting specific machines. There's a whole query language to target machines. And that's kind of what Serf is. I'll skip that. But the result basically is when you build with this sort of thing in mind, you build a huge resiliency to failure because you're expecting that your application can learn about failures or joins and membership in milliseconds, and that change allows adaptation. So it's really just a mindset sort of thing. And we're working on a little something, we're really focused on this sort of orchestration aspect right now in terms of tooling. So we're working on a little bit more. And so just to tease you, this is just the logo of something else we have coming out in about 2 weeks. You could try to guess. It starts with C. Yeah. Okay. So I'm out of time. So we're just going to... so the point really of this talk is that DevOps moves really, really fast. And there's a lot of tools coming out now, and they're really interesting. They're all really interesting. But sometimes, especially don't work in ops all the time, it's pretty confusing of where they apply. But the good news is that there's a really clear problem set of what these DevOps tools solve. And it has to be somewhere in here. It has to be one or more things in here. And if you really, print this thing out or something and start marking off what tools you use where, you could really get a pretty clear picture of whether you need a new tool or whether a new tool will solve a problem you have, whether you're replacing another tool or putting something next to it. It's really useful. And kind of as a final analogy, I like to say, we start with things like this, graves. And because of tools, this took, I forgot how many years now, but, let's say 80 years to build. It took like 80 plus, 100 plus years to build one of these pyramids. But nowadays we could build something very similar and quite large in scale in a year or two. And that's really because of tools. So, and that's a grave too, because it's a museum. So, and that's it. So thank you. And you can learn more about the technical side of things at the other talks later today. And that's it. Thanks.